Welcome back to the School of Nap. Class is in session. Tonight's lecture takes us on a journey through our cosmic neighborhood, the solar system. From the blazing heat of the sun to the frozen darkness beyond Neptune, we'll explore the planets, moons, and mysteries that share our corner of space. Get comfortable. Adjust your pillows. Let your body sink into whatever surface supports you. There's no test tomorrow, no notes to take. Your mind can simply wander among the worlds we'll visit tonight. Let's begin. Right now, as you lie here, you're moving through space at extraordinary speeds. Though you feel perfectly still, you're not just sitting on Earth. You're riding on a planet that spins on its axis at over 1,600 kilometers per hour at the equator. That's faster than the speed of sound. And while Earth spins, it also orbits the Sun at about 107,000 kilometers per hour. That's roughly 30 kilometers every second. Imagine traveling from your house to the next town over, completed in a single second.
And the Sun itself isn't stationary. It's orbiting the center of the Milky Way galaxy at roughly 790,000 kilometers per hour, carrying the entire solar system with it. You are traveling through space right now at speeds that would make any spacecraft we've ever built look like it's standing still. Yet you feel none of this motion. You're simply here, resting, while the universe moves around you.
The solar system is our home, but it's just one tiny system among hundreds of billions in our galaxy. Picture a grain of sand on a beach. That grain is our solar system. The beach is the Milky Way. And there are more beaches than you could count in a lifetime. But tonight, we're staying close to home. We're exploring our own grain of sand. And even this small corner of space contains wonders enough to fill a lifetime of study. Take a breath. We have all night. Let's start at the center, with the Sun. The Sun is the reason you exist. Every bit of warmth you've ever felt, every plant that's ever grown, every breath of oxygen you've taken, all of it traces back to the Sun. It's the heart of the solar system, and everything else, every planet, every moon, every asteroid, orbits around it. The Sun is a star, and not a particularly special one. It's a yellow dwarf, average in size, average in temperature, average in just about every way. In a galaxy of hundreds of billions of stars, the Sun would never stand out. But it's our star, and from our perspective, it's everything. Think about what the Sun actually is. It's a ball of plasma, a state of matter so hot that atoms are torn apart into their component particles. The temperature at the core reaches 15 million degrees Celsius. At those temperatures, the rules that govern matter in our everyday world break down completely. There are no solids, no liquids, not even gases as we understand them. Just a roiling sea of particles moving at incredible speeds, colliding, fusing, releasing energy. The Sun's surface, what we call the photosphere, is much cooler by comparison, only about 5,500 degrees Celsius. Only. That's still hot enough to vaporize any known material instantly. The photosphere is what we see when we look at the sun, though you should never look directly at it without proper protection. The light is so intense, it can permanently damage your eyes in seconds. Above the photosphere lies the chromosphere, a layer of the atmosphere that glows with a reddish hue during solar eclipses. And above that, the corona, the sun's outer atmosphere, extends millions of kilometers into space. Strangely, the corona is hotter than the surface, reaching temperatures of over 1,000,000 degrees. Why the corona is so hot remains one of the mysteries of solar physics. The heat should dissipate as you move away from the source, but in the sun's case, it increases. Scientists think magnetic fields play a role, channeling energy outward, but the exact mechanism is still debated. The sun isn't a solid object, so different parts rotate at different speeds. The equator completes a rotation in about 25 days, while regions near the poles take about 35 days. This differential rotation twists and tangles the sun's magnetic field, creating regions of intense magnetic activity. These appear as sunspots, dark patches on the surface that are cooler than their surroundings, though still thousands of degrees hot. Sunspots come and go in an 11-year cycle. During solar maximum, the sun is covered with spots and experiences frequent solar flares and coronal mass ejections, violent eruptions that blast billions of tons of charged particles into space. During solar minimum, the sun is quieter, with few or no spots. We're currently in solar cycle 25, which began in 2019 and will peak sometime in the mid-2020s. When charged particles from solar flares reach Earth, they interact with our magnetic field, creating auroras, the northern and southern lights. These shimmering curtains of green, red, and purple light dance across the polar skies, a visible reminder of the sun's influence on Earth. If you've ever seen an aurora, you've witnessed the sun's power directly. Particles that left the sun days earlier, colliding with Earth's atmosphere at thousands of kilometers per second. Take a moment to picture the sun not as a flat yellow circle in the sky, but as a three-dimensional sphere of plasma larger than 1,000,000 Earths, burning through fusion, spinning, erupting, flooding the solar system with light and heat and charged particles. It's been doing this for over 4.5 billion years, and it will continue for billions more. The sun contains 99.8% of all the mass in the solar system. Jupiter, the largest planet, is 1,000 times less massive. Earth is over 300,000 times less massive. If you gathered up all the planets, all the moons, all the asteroids, all the comets, all the dust and gas floating between the worlds, and combine them into one object, the sun would still be over 700 times more massive. To give you a sense of scale, imagine the sun as a large beach ball, about 1 meter across. Earth, on that scale, would be the size of a small peppercorn. Jupiter would be the size of a grape. And the distance from Earth to the sun would be about 107 meters. Picture walking the length of a football field. That's the scale of our solar system when the sun is a beach ball. The sun is made almost entirely of hydrogen and helium, the two simplest and lightest elements.
At its core, where the temperature reaches 15 million degrees Celsius, hydrogen atoms are crushed together so tightly that they fuse, combining into helium and releasing enormous amounts of energy. This is nuclear fusion, the same process that powers hydrogen bombs, but controlled and sustained over billions of years. Every second, the sun converts about 600 million tons of hydrogen into helium, and every second, about 4 million tons of matter are converted directly into energy, following Einstein's equation E equals mc squared. That energy radiates outward as light and heat, traveling through space, reaching Earth in about 8 minutes. When you feel the warmth of sunlight on your face, you're feeling energy that was created in the heart of the sun just minutes ago, though actually the story is more complicated. The photons of light created in the sun's core don't travel straight out. They bounce around inside the sun, absorbed and re-emitted countless times, taking a random zigzagging path through the dense plasma. This journey from the core to the surface takes roughly 170,000 years. So in a sense, the sunlight you feel today began its journey long before human civilization existed. The sun has been shining steadily for about 4.6 billion years. It formed from a collapsing cloud of gas and dust, the same cloud that gave birth to the planets. And it will continue to shine for another 5 billion years or so, gradually growing hotter and brighter. Eventually it will swell into a red giant, engulfing the inner planets. But that's so far in the future that it might as well be forever. For now, the sun is stable, reliable, the constant anchor of our existence. Let that sink in for a moment. The sun burning steadily, unchanging from our perspective, the source of all warmth and light. Now, take a breath. Rest your thoughts there for a moment. Now let's move outward from the sun and visit the worlds that orbit it. We'll start with the closest planet, a scorched, cratered world where the sun looms 3 times larger in the sky than it does from Earth. Mercury is the smallest planet in the solar system and the closest to the sun. It's a tiny, barren world, just slightly larger than Earth's moon. If you stood on Mercury's surface, the sun would dominate the sky, enormous and blinding, pouring down heat and radiation with no atmosphere to soften it. Mercury orbits the sun at an average distance of about 58 million kilometers. That might sound far, but it's less than 40% of Earth's distance from the sun. At that proximity, the sun's heat is intense. During the day, Mercury's surface temperature can reach 430 degrees Celsius. That's hot enough to melt lead, hot enough to turn zinc into a puddle. But Mercury has no atmosphere to trap and distribute heat. Without that insulating blanket, the heat doesn't spread around the planet or linger into the night. So when the sun sets on Mercury, temperatures plummet dramatically. At night, temperatures drop to minus 180 degrees Celsius. That's colder than the coldest temperature ever recorded on Earth, colder than liquid nitrogen. The difference between day and night on Mercury is over 600 degrees. Imagine standing in an oven, then stepping into a freezer, colder than anything on Earth. That's Mercury's daily cycle. Mercury's orbit is strange in several ways. It takes 88 Earth days to complete one orbit around the Sun, making it the fastest orbiting planet. The name Mercury comes from the Roman messenger god, known for his speed. But despite its quick orbit, Mercury rotates very slowly. It takes about 59 Earth days for Mercury to complete one full rotation on its axis. This creates an unusual relationship between Mercury's day and year. Because of the way Mercury's rotation and orbit sync up, one full day on Mercury, from sunrise to sunrise, actually takes 176 Earth days. That's 2 Mercury years. Think about that for a moment. You could orbit the Sun twice before experiencing a single sunrise and sunset. If you stood in one spot on Mercury and watched the Sun, it would take nearly 3 Earth months to crawl slowly from horizon to horizon across the sky. And because Mercury's orbit is elliptical, not perfectly circular, its speed around the Sun varies. When it's closer to the Sun, it moves faster. When it's farther away, it slows down. This creates an optical illusion from the surface. At certain points in Mercury's orbit, if you were standing in the right location, you would see the Sun rise partway above the horizon, then stop, reverse direction and set again, then rise once more and continue across the sky. The Sun would appear to move backward for a while. This retrograde motion is caused by Mercury speeding up and slowing down as it follows its elliptical path. It would be a disorienting, dreamlike experience watching the Sun stutter and backtrack across the alien sky. Mercury's surface tells the story of billions of years of violence. It's heavily cratered, every impact from asteroids and meteorites permanently recorded. There's no atmosphere to burn up incoming objects, no water or wind to erode the scars. The surface looks ancient, frozen in time. The largest crater, the Caloris Basin, is truly enormous, about 1,500 kilometers across. That's roughly the distance from London to Rome or from New York to Denver. The impact that created Caloris was so powerful that it sent shockwaves rippling through the entire planet. On the exact opposite side of Mercury, those shockwaves converged, creating strange jumbled terrain called chaotic terrain or weird terrain. The ground was literally shaken apart by an impact on the other side of the world. Mercury has a large iron core, making up about 61% of the planet's volume. That's much larger proportionally than Earth's core. One theory suggests that Mercury was once much larger, but a massive collision early in its history stripped away much of its rocky outer layers, leaving behind the dense core and a thin shell of rock. Mercury is what remains. A planetary core with just a thin skin. Despite being the closest planet to the Sun, Mercury isn't the hottest planet in the solar system. That distinction belongs to Venus, our next destination. But Mercury holds its own mysteries. Deep craters near its poles, places that never see sunlight, appear to contain water ice. Yes, ice. On a planet where the sunlit surface is hot enough to melt metal.
These permanently shadowed craters are colder than most of the outer solar system. Sunlight never reaches their floors, so temperatures stay perpetually below minus 170 degrees Celsius. Radar observations from Earth and measurements from spacecraft suggest these craters hold deposits of water ice, perhaps delivered by comets that crashed into Mercury long ago. The ice has remained frozen for potentially billions of years, hidden in eternal darkness, while just a few kilometers away, the surface bakes under the intense sun. Mercury has no moons, no rings, no atmosphere. Just a small, lonely world orbiting close to the furnace of the sun, spinning slowly, baking on one side while freezing on the other. Let your mind rest on that image for a moment. A tiny planet caught between extremes, marked by eons of impacts, harboring ice in its darkest shadows. Now let's move outward to the second planet, a world shrouded in clouds and mystery. Venus is often called Earth's twin because the two planets are similar in size and mass. Venus is about 95% Earth's diameter and 80% its mass. From a distance, they look like siblings. But if Earth is a garden, Venus is a furnace. Venus orbits the Sun at about 108 million kilometers, about 70% of Earth's distance. It should be warmer than Earth, but not dramatically so. Yet Venus is the hottest planet in the solar system, with surface temperatures averaging 467 degrees Celsius. That's hotter than Mercury, despite being nearly twice as far from the Sun. The reason is Venus's atmosphere. It's incredibly thick, about 90 times denser than Earth's atmosphere. Standing on Venus would feel like being deep underwater, the pressure crushing down from all sides. And that atmosphere is mostly carbon dioxide, a powerful greenhouse gas. Sunlight passes through the atmosphere and warms the surface, but the heat can't escape back into space. It's trapped, building up and up, until the entire planet is hotter than an oven. The clouds that shroud Venus aren't water clouds. They're made of sulfuric acid. Yes, the same acid used in car batteries, hanging in thick, yellowish clouds that completely hide the surface from view. These clouds reflect most of the sunlight that hits them, making Venus one of the brightest objects in our sky after the sun and moon. But beneath those clouds, conditions are hellish. Venus rotates extremely slowly and in the opposite direction from most planets. While Earth rotates counterclockwise as viewed from above the North Pole, Venus rotates clockwise. We say it has retrograde rotation. One full rotation takes 243 Earth days. That's longer than Venus's year, which is only 225 Earth days. So on Venus, a day is longer than a year. And because of its retrograde rotation, the sun rises in the west and sets in the east, the opposite of Earth. The surface of Venus is hidden beneath the clouds, but radar imaging from spacecraft has revealed a landscape of volcanic plains, massive mountain ranges, and thousands of volcanoes. Some of these volcanoes may still be active, though confirming this is difficult.
The thick atmosphere makes it nearly impossible for spacecraft to survive on the surface for more than a few hours before the heat and pressure destroy them. Venus may not have always been this way. Some scientists think Venus once had oceans, liquid water covering much of its surface, perhaps even conditions suitable for life. But something went wrong. A runaway greenhouse effect turned the planet into the inferno it is today. The water boiled away, the atmosphere thickened, and Venus became a cautionary tale about what can happen when a planet's climate spirals out of control. Despite the harsh conditions, Venus continues to fascinate scientists. Recent discoveries suggest the possibility of microbial life floating in the clouds, where temperatures and pressures are more moderate. Certain chemicals detected in the atmosphere are difficult to explain without biological processes. It's speculative and far from proven, but it raises the tantalizing possibility that life might exist even in the clouds of hell. Venus has no moons and no rings, just endless crushing heat and pressure beneath a perpetual blanket of acid clouds. Picture it for a moment, a world that might once have been like Earth, now transformed into something utterly hostile. Let that image settle as we move to the third planet, the only one we know for certain harbors life. Earth is the third planet from the Sun, orbiting at an average distance of 150 million kilometers. This distance is so commonly referenced in astronomy that it has its own name, 1 astronomical unit, or AU. It's the measuring stick we use for the solar system. When astronomers say Jupiter is 5 astronomical units from the Sun, they mean it's 5 times farther than Earth. From space, Earth is instantly recognizable. Blue oceans cover 70% of the surface. White clouds swirl in constantly shifting patterns. Green and brown land masses peek through, though not as much green as you might think. Most of the vegetation is concentrated in certain regions: the tropical rainforests, temperate forests, grasslands. From space, much of the land appears brown or tan, deserts and dry regions that cover surprising amounts of the continents. But it's the blue that stands out. Earth is the only planet in the solar system with liquid water on its surface. Mars probably had water billions of years ago, and some moons have subsurface oceans, but only Earth has vast oceans, lakes, and rivers exposed to the atmosphere. This water is why life exists here. Earth is the largest of the inner rocky planets, with a diameter of about 12,742 kilometers. If you walked around Earth's equator, you'd travel just over 40,000 kilometers. At a brisk walking pace of 5 kilometers per hour, walking 8 hours a day, it would take you about a year of continuous walking. Of course, you'd have to figure out how to walk across oceans, but the point stands. Earth is large enough that circumnavigating it on foot, even theoretically, would be a monumental journey. What makes Earth unique isn't its size or position, though both are important. It's the combination of factors that allow life to thrive. The atmosphere is breathable, temperatures are moderate, liquid water is abundant, and perhaps most importantly, Earth has remained stable enough for long enough for life to evolve from single-celled organisms to the incredible diversity we see today. Earth's atmosphere is mostly nitrogen, about 78%, with 21%
oxygen, and trace amounts of other gases like argon, carbon dioxide, and water vapor. The oxygen is particularly important because it's a product of life. For the first 2 billion years of Earth's history, there was almost no oxygen in the atmosphere. Then photosynthetic organisms evolved, first cyanobacteria, later plants and algae, and they began releasing oxygen as a waste product. This gradual oxygenation of the atmosphere, sometimes called the Great Oxygenation Event, was actually catastrophic for many early life forms. Oxygen was toxic to them, but it opened the door for new forms of life that could use oxygen to extract energy more efficiently from food. Eventually, complex multicellular life evolved, and here we are. The atmosphere does more than provide air to breathe. It protects the surface from harmful solar and cosmic radiation. It regulates temperature, preventing the extreme swings that occur on airless worlds like Mercury. And it creates weather, the movement of air and water vapor that distributes heat and moisture around the planet. Weather is driven by the sun's uneven heating of Earth's surface. The equator receives more direct sunlight than the poles, creating temperature differences. Warm air rises, cool air sinks. And this creates circulation patterns, convection cells that move air around the globe. Add in Earth's rotation and you get prevailing winds, jet streams, and the complex weather systems that bring rain, snow, storms, and clear skies. The water cycle is fundamental to Earth's climate and life. Water evaporates from oceans, lakes, and soil, rising into the atmosphere as vapor. It condenses into clouds, then falls as precipitation, rain, or snow. Some of that water runs off into rivers and returns to the ocean. Some soaks into the ground, replenishing aquifers. Some is taken up by plants, used in photosynthesis, then released back into the air through transpiration. This cycle has been operating for billions of years, powered by the sun's energy. Earth has one large moon, simply called the Moon, about 1/4 Earth's diameter. The Moon is unusually large compared to its planet. Most moons in the solar system are tiny compared to their planets, but the Moon is substantial. If Earth were the size of a basketball, the Moon would be the size of a tennis ball, orbiting about 7 meters away. That's a much closer and larger companion than most planets have. The Moon's origin is dramatic. About 4.5 billion years ago, when Earth was still young and molten, a Mars-sized object, sometimes called Theia, collided with Earth. The impact was unimaginably violent, vaporizing and ejecting enormous amounts of material into orbit. This debris, a mix of material from Earth and the impactor, eventually coalesced into the Moon. Evidence for this giant impact hypothesis comes from the Moon's composition, which is similar to Earth's mantle, but lacks a large iron core, and from computer simulations showing such a collision could produce a moon like ours. The Moon's presence has profoundly influenced Earth's evolution. Its gravity creates tides, the rhythmic rising and falling of ocean levels. Tides have shaped coastal ecosystems for billions of years. They may have played a role in the origin of life, creating tidal pools where concentrations of organic molecules could interact and eventually give rise to the first living cells. Tides also gradually slow Earth's rotation. Days are getting longer, though imperceptibly, about 1.7 milliseconds per century. Billions of years ago, Earth's day was much shorter, perhaps only 10 hours long.
The moon also stabilizes Earth's axial tilt. Without the moon's gravitational influence, Earth's tilt would vary chaotically over millions of years, causing wild swings in climate. Mars, which has 2 tiny moons with negligible gravitational influence, experiences such variations. Its tilt can change from near zero to over 60 degrees, causing dramatic climate shifts. Earth's relatively stable tilt, held steady by the moon, has allowed a more predictable climate, perhaps making the evolution of complex life more likely. Earth rotates once every 24 hours, creating the familiar cycle of day and night. It orbits the Sun once every 365.25 days, which is why we need a leap year every 4 years to keep our calendar aligned with the seasons. Earth's axis is tilted about 23.5 degrees relative to the plane of its orbit, and this tilt gives us seasons. When the northern hemisphere tilts toward the sun, it experiences summer, more direct sunlight, and longer days. 6 months later, when it tilts away, it experiences winter, less direct sunlight, and shorter days. The southern hemisphere experiences opposite seasons. Beneath Earth's surface lies a complex, layered structure. The crust, the thin outermost layer, is where we live. It ranges from about 5 kilometers thick under the oceans to up to 70 kilometers thick under mountain ranges. Beneath the crust is the mantle, a thick layer of hot, semi-solid rock, about 2,900 kilometers deep. The mantle is not liquid, but over geological time, it flows slowly, like very thick honey, driven by heat from below. Below the mantle lies the core, divided into 2 parts. The outer core is liquid iron and nickel, about 2,200 kilometers thick. The motion of this liquid metal, driven by Earth's rotation and heat from the inner core, generates Earth's magnetic field. This magnetic field extends far into space, creating a protective bubble called the magnetosphere. It deflects most of the charged particles streaming from the sun, the solar wind, protecting our atmosphere and surface from erosion and radiation. Without this magnetic shield, Earth might have lost its atmosphere long ago, as Mars did. The inner core is solid iron and nickel, despite being hotter than the outer core, because the immense pressure at Earth's center forces the metal to remain solid. The inner core is about 1,200 kilometers in diameter, roughly 3/4 the size of the moon. Temperatures there reach about 5,400 degrees Celsius, about as hot as the surface of the sun. Earth's crust is broken into tectonic plates, massive slabs of rock that float on the semi-fluid mantle beneath. These plates move very slowly at rates of a few centimeters per year, about as fast as your fingernails grow. But over millions of years, this movement reshapes the planet. Plates collide, creating mountain ranges like the Himalayas. They pull apart, creating rifts and new ocean floor. They slide past each other, causing earthquakes along faults like the San Andreas. Volcanoes erupt where plates subduct, one plate diving beneath another, melting and rising as magma. This plate tectonics is unique to Earth among the rocky planets. Venus and Mars show no signs of plate tectonics. Their surfaces are largely static, shaped by volcanism and impacts, but not by the constant recycling that characterizes Earth. Plate tectonics helps regulate Earth's climate. by recycling carbon dioxide. When rocks weather, they absorb CO2 from the atmosphere. This carbon is eventually subducted and released through volcanoes, maintaining a balance. Without this cycle, Earth's climate might have gone to extremes long ago, either freezing over completely or heating up like Venus. Life on Earth is staggeringly diverse. Scientists have identified and named about 1.2 million species, but estimates suggest there may be 8 to 10 million species in total, possibly more. These species inhabit every conceivable environment. Bacteria live in boiling hot springs and frozen Antarctic lakes. Fish thrive in the deepest ocean trenches where pressure would crush a human instantly. Plants grow on the highest mountain peaks, in the driest deserts, and everywhere in between. Life is persistent, adaptable, and endlessly creative. You are part of this living planet, one species among millions, yet unique in your ability to contemplate your place in the cosmos. Right now, you're resting on Earth's surface, held by gravity, breathing its atmosphere, warmed by its sun. Now let's continue outward to the fourth planet, a world that may once have been more like Earth than it is now. Mars is the fourth planet from the Sun, orbiting at about 228 million kilometers, roughly 1.5 times Earth's distance. It's a small world, about half the diameter of Earth, with a thin atmosphere and a cold, desert-like surface. From Earth, Mars appears as a reddish point of light, and for centuries, humans have been fascinated by it. The red color comes from iron oxide, essentially rust, covering much of the surface. Mars is a rusty planet, its rocks and soil oxidized over billions of years. During the day, temperatures near the equator can reach a pleasant 20 degrees Celsius, but at night, they plummet to minus 73 degrees Celsius. The thin atmosphere, mostly carbon dioxide, provides almost no insulation. Mars has the largest volcano in the solar system, Olympus Mons. It's about 625 kilometers across at its base and rises 21 kilometers above the surrounding plains. That's nearly 2.5 times the height of Mount Everest. If you stood at the summit of Olympus Mons and looked down, the horizon would curve away in all directions, the base of the volcano disappearing over the planet's curvature. The slopes are so gradual that you could walk up them without realizing you were climbing a mountain. It would just seem like endless, gently rising terrain. Mars also has the largest canyon system in the solar system, Valles Marineris. This enormous rift stretches about 4,000 kilometers, nearly a quarter of the way around Mars. It's up to 7 kilometers deep in places. If Valles Marineris were on Earth, it would stretch from New York to Los Angeles. Standing on one rim, the other side would be beyond the horizon, invisible. It would feel less like a canyon and more like the edge of the world. Mars has 2 small moons, Phobos and Deimos, both irregularly shaped and heavily cratered. They're probably captured asteroids pulled into orbit around Mars long ago. Phobos is the larger of the two, but still tiny, only about 22 kilometers across. It orbits so close to Mars that it's gradually spiraling inward. In about 50 million years, Phobos will either crash into Mars or be torn apart
by tidal forces forming a ring around the planet. Mars is cold and dry now, but it wasn't always this way. The surface is covered with features that strongly suggest liquid water once flowed there. Ancient river valleys, deltas, lake beds, and minerals that only form in the presence of water all point to a wetter past. Billions of years ago, Mars likely had a thicker atmosphere and a warmer climate, with rivers, lakes, and perhaps even an ocean covering part of the northern hemisphere. What happened? Mars is smaller than Earth with weaker gravity. Its atmosphere gradually leaked away into space, carried off by the solar wind. Without a strong magnetic field to protect it, Mars couldn't hold on to its air. As the atmosphere thinned, the water evaporated or froze. Today, water exists on Mars primarily as ice, locked in the polar ice caps and buried beneath the surface. The possibility that Mars once had liquid water raises an intriguing question. Could life have emerged there? On Earth, wherever there's liquid water, there's life. If Mars had rivers and lakes for millions or even billions of years, perhaps simple life forms evolved. They might have gone extinct when the planet dried out, or they might still exist deep underground, where conditions could be more hospitable. Spacecraft have been exploring Mars for decades, searching for signs of past or present life. So far, no definitive evidence has been found, but the search continues. Future missions plan to return samples from Mars to Earth, where they can be analyzed in detail. If life ever existed on Mars, even microbial life, it would revolutionize our understanding of biology and our place in the universe. Mars has fascinated humans for centuries, inspiring countless stories of Martian civilizations and alien invasions. In reality, Mars is a cold, dusty desert, silent and still. But it's also the planet most like Earth in the solar system, and it might hold answers to profound questions about life beyond our world. Picture Mars for a moment. A red desert stretching to the horizon, ancient valleys carved by long vanished rivers, and above, two small moons racing across a butterscotch sky. Now let your thoughts drift outward, past Mars, into the space between the rocky inner worlds and the realm of the giants. Here, in this transitional zone, we encounter a region that's neither planet nor empty space. A band of ancient debris tumbling through the darkness, remnants of a world that never came to be. This is the Asteroid Belt. Between Mars and Jupiter lies a region of space filled with rocky debris, the Asteroid Belt. This isn't a dense field of constantly colliding rocks, like in science fiction movies. The asteroids are spread out over an enormous volume. If you were flying through the asteroid belt, you'd likely go days or weeks without seeing one. Space is vast, even here. The asteroid belt contains millions of rocky objects, ranging from tiny pebbles to dwarf, planet-sized bodies hundreds of kilometers across. The largest, Ceres, is about 950 kilometers in diameter, roughly the size of Texas. Ceres is classified as a dwarf planet now, the only one in the inner solar system. All the asteroids combined have only about 4% of the moon's mass. If you gathered them all together, they wouldn't form a planet. There's simply not enough material. In fact, the asteroid belt might be the remnant of a planet that never formed. When the solar system was young, Jupiter's powerful gravity likely prevented the material in this region from coalescing into a single world. Instead, it remained scattered, a failed planet. Most asteroids are irregular, potato-shaped rocks. Tumbling through space, they're covered with craters from impacts with other asteroids. Some are solid rock. Others are loose collections of rubble held together weakly by gravity, called rubble piles. A few asteroids are actually metal, the exposed iron cores of larger bodies that were shattered by collisions. Some asteroids have their own moons, tiny companions, orbiting even tinier primaries. A few asteroids are binary systems, two similar-sized objects orbiting each other. It's a chaotic, fascinating region, a snapshot of the early solar system, frozen in time. Asteroids occasionally collide with Earth. Small ones burn up in the atmosphere as meteors shooting stars. Larger ones can survive the atmosphere and hit the ground as meteorites. Very large impacts are rare but catastrophic. The asteroid that struck Earth 66 million years ago, ending the age of dinosaurs, was only about 10 kilometers across, but its impact released energy equivalent to billions of nuclear bombs. It created a crater 180 kilometers wide and triggered global climate changes that wiped out 3/4 of all species. Fortunately, such impacts are rare. We're now capable of detecting most large asteroids that might pose a threat, and in theory, we could deflect one if we had enough warning. The asteroid belt itself poses no danger. It's far from Earth, and the asteroids there will remain there, orbiting the Sun for billions of years. Let your thoughts drift through this field of ancient rock, remnants of the solar system's formation tumbling silently in the space between the small rocky planets and the giant worlds beyond. Now let's cross that boundary and visit the king of planets. Jupiter is enormous. It's the largest planet in the solar system by far, so large that all the other planets combined could fit inside it with room to spare. Jupiter is about 11 times Earth's diameter. If Earth were the size of a grape, Jupiter would be the size of a basketball. In terms of mass, Jupiter contains more than twice the mass of all the other planets combined. It's a giant among giants. To give you a better sense of Jupiter's scale, imagine this. The Great Red Spot, that massive storm on Jupiter's surface, is about 16,000 kilometers wide. Earth's diameter is about 12,700 kilometers. That means the Great Red Spot is wider than Earth. You could fit our entire planet inside that storm, with room left over. And the storm has been raging for at least 350 years, possibly much longer. That's not a brief weather event. It's a permanent feature. A storm that's older than the United States, older than the Industrial Revolution, outlasting empires and civilizations. Jupiter orbits the Sun at about 778 million kilometers, more than 5 times Earth's distance. At that distance, sunlight takes about 43 minutes to travel from the Sun to Jupiter. Sunlight is 25 times fainter than on Earth. Yet, despite receiving so much less energy,
Jupiter remains a bright object in our night sky, easily visible even from light-polluted cities. That's because Jupiter is so large and its clouds so reflective that it bounces back enormous amounts of light. Jupiter is a gas giant, meaning it doesn't have a solid surface like Earth or Mars. If you tried to land a spacecraft on Jupiter, there would be no place to land. You would simply descend deeper and deeper into increasingly dense gas and liquid. The pressure and temperature rising steadily until your spacecraft was crushed and vaporized, long before reaching anything resembling a core. The planet is composed mostly of hydrogen and helium, the same elements that make up the Sun, though Jupiter never had enough mass to ignite fusion and become a star. It's been estimated that if Jupiter were about 80 times more massive, it would have ignited as a brown dwarf, a failed star that generates some heat but not true stellar fusion. The visible surface of Jupiter is actually the top of its cloud layers, a turbulent atmosphere of swirling storms and colorful bands. The colors come from chemical compounds in the clouds, sulfur, phosphorus, and organic molecules created by lightning and ultraviolet light from the sun. The bands themselves are created by powerful jet streams, winds that blow at hundreds of kilometers per hour in alternating directions at different latitudes. The light-colored bands are called zones. In these regions, warm gas rises from deep in the atmosphere, cools as it reaches higher altitudes, and forms high-altitude clouds. The darker bands are called belts, where cooler gas sinks back down into the planet. This pattern of rising and sinking gas, driven by Jupiter's internal heat and rapid rotation, creates the banded appearance that makes Jupiter so recognizable. Jupiter rotates faster than any other planet in the solar system. One complete rotation takes only about 9 hours and 55 minutes. That means Jupiter's day is less than 10 hours long, despite the planet being over 11 times wider than Earth. This rapid rotation causes Jupiter to bulge noticeably at the equator. If you could measure Jupiter precisely, you'd find it's about 9,000 kilometers wider at the equator than from pole to pole. It's not a perfect sphere, but an oblate spheroid, flattened at the poles and wider at the middle, the result of centrifugal force from its rapid spin. Jupiter's internal structure is still somewhat mysterious because we can't directly observe it, but models based on the planet's mass, size, and gravitational field give us a picture. The outer layers are gaseous, hydrogen, and helium. Deeper down, pressure increases and the hydrogen transitions to liquid. Deeper still, at pressures millions of times Earth's atmospheric pressure, hydrogen becomes metallic, a strange state where it conducts electricity like a metal despite being hydrogen. This metallic hydrogen layer, thousands of kilometers thick, is thought to be where Jupiter's powerful magnetic field is generated. At Jupiter's core, if there is a distinct core, there's probably a mixture of rock, metal, and hydrogen compounds, perhaps 10 to 20 times Earth's mass, compressed to unimaginable densities and heated to tens of thousands of degrees. But the core is so deep and the conditions so extreme that we may never directly confirm its composition. Jupiter generates more heat than it receives from the Sun. If you could measure the infrared radiation coming from Jupiter, you'd find it's radiating about 1.7 times more energy than it absorbs from sunlight. Where does this extra heat come from? Primarily from gravitational contraction. Jupiter's still very slowly shrinking, just a few centimeters per year, but this gradual contraction converts gravitational potential energy into heat. It's been doing this since it formed, and it will continue for billions of years. Jupiter has a powerful magnetic field, the strongest of any planet, about 20,000 times stronger than Earth's. This magnetic field extends millions of kilometers into space, creating a magnetosphere so large that if you could see it from Earth, it would appear larger than the full moon. The magnetosphere traps charged particles from the solar wind, creating intense radiation belts around Jupiter. These belts are so deadly that spacecraft passing through them must be heavily shielded to avoid damage to their electronics. Jupiter's magnetosphere also interacts with its moons, particularly Io. As Io orbits through Jupiter's magnetic field, it generates enormous electrical currents, millions of amps flowing between the moon and the planet. These currents produce auroras at Jupiter's poles, similar to Earth's northern and southern lights, but vastly more powerful. Jupiter's auroras are permanent features, glowing continuously with more energy than all of Earth's power generation. Jupiter has at least 95 known moons, and more are being discovered regularly as our telescopes and detection methods improve. Most of these moons are small, irregular chunks of rock and ice, probably asteroids, captured by Jupiter's immense gravity. But 4 of Jupiter's moons are large, fascinating worlds in their own right. These are the Galilean moons, named after Galileo Galilei, who discovered them in 1610 with one of the first telescopes. The discovery of the Galilean moons was revolutionary. It proved that not everything in the universe orbited Earth. Here were 4 moons clearly orbiting Jupiter, visible to anyone with a telescope. This was powerful evidence for the Copernican model of the solar system, where planets orbit the sun rather than Earth. Galileo's observations, along with those of other astronomers, helped shift humanity's understanding of its place in the cosmos. Io, the innermost Galilean moon, is one of the most geologically active bodies in the solar system. Its surface is covered with hundreds of active volcanoes, constantly erupting, spewing sulfur, sulfur dioxide, and silicate rock hundreds of kilometers into space. Io has no impact craters because volcanic activity constantly resurfaces the moon, burying old craters under fresh lava. Io's volcanism is driven by tidal heating, a process unique among solid bodies. Io orbits Jupiter in a slightly elliptical orbit, influenced by the gravitational pull of the other Galilean moons. As Io moves closer to and farther from Jupiter, the planet's immense gravity stretches and squeezes the moon. This constant flexing generates internal friction, melting rock, and driving volcanic activity. It's estimated that Io's interior is partially molten, with a magma ocean beneath the crust. The surface of Io is a hellscape of lava lakes, sulfur plains, and mountains taller than Mount Everest. Plumes of gas and particles erupt continuously, visible from space. Some of these plumes reach altitudes of over 300 kilometers. The volcanic activity also creates Io's thin atmosphere, mostly sulfur dioxide, which freezes out onto the surface when Io moves into Jupiter's shadow, creating frost, then sublimates back into gas when Io returns to sunlight. Europa, the next moon outward, is completely different. It's covered in a thick shell of water ice that appears smooth and relatively young with few craters. The surface is crisscrossed with long, linear fractures and ridges, suggesting the ice is constantly shifting and breaking. The ice shell is estimated to be 10 to 30 kilometers thick, but beneath it, scientists believe there's a global ocean of liquid water, perhaps 100 kilometers deep. This subsurface ocean is kept liquid by tidal heating, similar to Io but less intense. Europa's ice shell insulates the ocean, keeping it from freezing despite being far from the sun. The ocean contains more water than all of Earth's oceans combined, and where there's liquid water, especially water in contact with rock at the ocean floor, there's potential for life. Europa is one of the highest priority targets in the search for extraterrestrial life. Future missions plan to orbit Europa, analyze plumes of water vapor that may erupt from the surface and eventually land and drill through the ice to access the ocean directly. If life exists in Europa's ocean, even simple microbial life, it would be one of the most profound discoveries in human history. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury. It has a diameter of about 5,260 kilometers compared to Mercury's 4,880 kilometers. Despite being a moon, Ganymede is geologically complex. It has its own magnetic field, the only moon known to have one, generated by a liquid iron core. Ganymede's surface is divided into two types of terrain: dark, heavily cratered regions that are ancient, dating back billions of years, and brighter grooved terrain that's younger and shows evidence of tectonic activity. Like Europa, Ganymede is thought to have a subsurface ocean, though buried deeper beneath multiple layers of ice and possibly high-pressure ice structures that don't exist on Earth. Callisto, the outermost Galilean moon, is heavily cratered, a relic of the early solar system when impacts were frequent. Its surface is ancient, among the oldest in the solar system, little changed for 4 billion years. Callisto is thought to have a subsurface ocean as well, though deeper and less accessible than Europa's. The moon's surface is a frozen record of the violence that characterized the solar system's youth. Every crater a testament to a collision that happened billions of years ago. Jupiter also has faint rings, though nothing like Saturn's spectacular system. Jupiter's rings are composed mostly of dust particles, probably ejected from small inner moons by micrometeorite impacts. The rings are so faint that they weren't discovered until 1979, when the Voyager 1 spacecraft imaged them. From Earth, they're nearly invisible, overwhelmed by Jupiter's brightness. Jupiter's gravity dominates the outer solar system. It acts like a cosmic shepherd, its immense gravitational pull influencing the orbits of asteroids and comets, sometimes sending them toward the inner solar system, other times flinging them out of the solar system entirely. Some scientists think Jupiter has protected Earth from many potential impacts over the eons, deflecting or capturing objects that might otherwise have struck our planet. In this sense, Jupiter is a guardian. Its gravity shielding the inner planets from some of the chaos of space. Picture Jupiter for a moment. A colossal world, more massive than everything else in the solar system combined, except the sun, spinning rapidly, banded with storms, its great red spot raging for centuries, surrounded by nearly 100 moons, 4 of which are worlds in their own right, a king among planets, and a reminder of the scale and power of the forces that shaped our solar system. If you're still with us, you're doing wonderfully, though honestly, at the school of nap, falling asleep is just as commendable as staying awake. There's no wrong answer here. Let that image settle as we move outward to the next giant, the one with the rings. Saturn is the 6th planet from the Sun, orbiting at about 1.4 billion kilometers, nearly 10 times Earth's distance. Like Jupiter, Saturn is a gas giant, composed mostly of hydrogen and helium, with no solid surface. But Saturn is most famous for one feature: its rings. Saturn's rings are the most spectacular in the solar system. They're vast, bright, and easily visible even through a small telescope. From edge to edge, the main ring system spans about 282,000 kilometers, but it's remarkably thin, in most places only about 10 meters thick. Imagine a disk the size of a large city, but only as thick as a 3-story building. That's the scale of Saturn's rings. The rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized chunks. Each particle orbits Saturn independently, following the laws of gravity. The rings aren't solid. They're more like a swarm of tiny moons, all moving together, creating the illusion of a solid structure. Why does Saturn have such prominent rings while other planets don't? We're not entirely sure. The rings might be the remnants of a moon that was torn apart by tidal forces or shattered by a collision, or they might be leftover material from Saturn's formation. Recent evidence suggests the rings might be relatively young, perhaps only a few 100 million years old, which would make them much younger than Saturn itself. The rings are divided into sections separated by gaps. The most prominent gap is the Cassini division, a dark band about 4,700 kilometers wide. It's not completely empty, but it has far fewer particles than the surrounding rings. The gap is caused by the gravitational influence of Saturn's moon Mimas. Particles in the Cassini division orbit Saturn at a rate that resonates with Mimas's orbit, and over time, Mimas's gravity clears them out. Saturn itself, like Jupiter, is a world of swirling clouds and powerful storms. Its atmosphere is layered in bands, though less colorful and distinct than Jupiter's. Wind speeds can reach 1,800 kilometers per hour near the equator, some of the fastest winds in the solar system. Saturn rotates rapidly, about once every 10.5 hours, causing it to bulge at the equator even more than Jupiter. It's the least dense planet in the solar system. If you could find an ocean large enough, Saturn would float. Of course, finding such an ocean is the tricky part. Saturn has at least 146 known moons, the most of any planet, though many are tiny, irregular objects. The largest moon, Titan, is bigger than the planet Mercury and is one of the most interesting worlds in the solar system. Titan has a thick atmosphere, thicker than Earth's, composed mostly of nitrogen, with a significant amount of methane. The surface pressure on Titan is about 1.5 times Earth's, so you could walk around without a pressure suit, though you'd still need oxygen and warmth. The temperature at the surface is minus 179 degrees Celsius, cold enough that water ice is as hard as rock. But Titan has liquid on its surface, not water, but liquid methane and ethane. These hydrocarbons form clouds, rain down onto the surface, and collect in lakes and seas. Titan has a complete liquid cycle, like Earth's water cycle. But with methane, there are rivers, lakes, and vast seas of liquid methane. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth. The possibility of life on Titan is intriguing but uncertain. The chemistry is alien, based on hydrocarbons rather than water, and the extreme cold slows chemical reactions drastically. But life, if it exists, might be adapted to these conditions in ways we can't yet imagine. Another fascinating moon is Enceladus, a small icy world about 500 kilometers across. Enceladus has geysers near its south pole that spray water ice and organic molecules into space. Beneath the icy crust lies a global ocean of liquid water, heated by tidal forces from Saturn. The geysers erupt through cracks in the ice, creating a faint ring around Saturn made of ice particles from Enceladus. The discovery of Enceladus's ocean and geysers makes it another prime target in the search for life. Spacecraft have flown through the geysers, analyzing the particles, and found not only water, but also organic molecules, the building blocks of life. Whether life exists there remains unknown, but the conditions seem favorable. Saturn is a jewel of the solar system, a giant world adorned with rings and surrounded by moons, some of which might harbor life. Picture it for a moment. The golden planet with its vast, delicate rings, casting shadows on itself, spinning silently in the depths of space. Take a breath here. Let your mind rest in Saturn's orbit for a moment. We've journeyed far from the sun, and we're about to venture even farther into realms where sunlight grows faint and worlds become strange in ways that challenge everything we know. When you're ready, we'll continue outward to the ice giants, planets colder and more mysterious still. Uranus is the seventh planet from the Sun, orbiting at about 2.8 billion kilometers, nearly 20 times Earth's distance. It's an ice giant, smaller than Jupiter and Saturn, but still massive, about 4 times Earth's diameter. Uranus is composed mostly of water, methane, and ammonia ices surrounding a rocky core. What makes Uranus truly unusual is its tilt. Most planets spin upright relative to their orbits, tilted by only a modest amount. Earth tilts 23.5 degrees, which gives us seasons. But Uranus tilts 98 degrees. It's essentially lying on its side, rolling along its orbit rather than spinning upright.
Imagine a spinning top that's fallen over but somehow keeps spinning as it rolls across a table. That's Uranus. This extreme tilt means Uranus has the most extreme seasons in the solar system. For part of its orbit, one pole points almost directly at the sun, bathing it in continuous sunlight for 42 Earth years. Then, as Uranus moves along its orbit, that pole gradually turns away and the other pole gets its turn. For 42 years, one hemisphere experiences endless day while the other endures endless night. Then they switch. No one knows for certain why Uranus tilts this way. The leading theory is that early in the solar system's history, Uranus was struck by a massive object, perhaps an Earth-sized protoplanet. The collision knocked Uranus onto its side. It's been rolling along ever since, a permanent reminder of the violence of the early solar system. Uranus appears as a pale blue-green disk in telescopes. The color comes from methane in its atmosphere, which absorbs red light and reflects blue and green. The atmosphere itself is remarkably bland compared to Jupiter and Saturn. There are few visible clouds or storms. The planet looks almost featureless, a smooth, uniform ball. But appearances can be deceiving. Recent observations have detected storms and clouds, suggesting the atmosphere is more active than it appears. Uranus has 13 known rings, though they're much fainter and narrower than Saturn's. They're composed mostly of dark particles, possibly organic compounds, darkened by radiation. The rings were discovered in 1977, when Uranus passed in front of a star, and the star's light briefly dimmed several times before and after the planet itself blocked the light. This revealed the presence of rings. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The largest, Titania and Oberon, are about 1,500 kilometers across. They're icy worlds, heavily cratered, with surfaces that show signs of past geological activity. One moon, Miranda, has some of the most bizarre terrain in the solar system. Its surface is a patchwork of different regions, cliffs up to 20 kilometers high, and strange, grooved terrain called corona. It looks like it was smashed apart and reassembled incorrectly. Uranus is cold and distant, a world turned on its side, rolling through the outer reaches of the solar system. Picture it for a moment, a pale blue sphere, its rings and moons circling perpendicular to its orbit, a lonely giant in the darkness. Let that image fade as we move to the outermost planet. Neptune is the 8th and final planet in the solar system, orbiting at about 4.5 billion kilometers, 30 times Earth's distance from the Sun. At that distance, sunlight is 900 times fainter than on Earth. Yet Neptune is still visible through telescopes, a deep blue world with an active atmosphere. Like Uranus, Neptune is an ice giant, composed of water, methane, and ammonia ices, around a rocky core. It's slightly smaller than Uranus, but more massive, suggesting it's more densely packed. The blue color, deeper than Uranus's, also comes from methane. But Neptune's atmosphere contains more methane and appears darker and richer in hue. Despite being the farthest planet from the Sun and receiving so little solar energy, Neptune has the fastest winds in the solar system. Wind speeds can exceed 2,000 kilometers per hour, far faster than any winds on Earth or even Jupiter. Why Neptune's atmosphere is so active when it receives so little energy from the Sun is a mystery. The planet must have a strong internal heat source, generating energy from deep within. Neptune's most famous feature was the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot, observed by Voyager 2 in 1989. The storm was about the size of Earth. But when the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot had disappeared. Other dark spots have appeared and vanished since then, suggesting Neptune's atmosphere is constantly changing. Neptune has 14 known moons. The largest, Triton, is particularly interesting. Triton is about 2,700 kilometers across, larger than Pluto, and it's one of the coldest objects in the solar system, with surface temperatures around minus 235 degrees Celsius. That's only 38 degrees above absolute zero, the coldest possible temperature. Triton orbits Neptune backward in a retrograde orbit, meaning it moves in the opposite direction from Neptune's rotation. This suggests Triton wasn't formed alongside Neptune but was captured, probably from the Kuiper Belt. The capture would have been gravitationally violent, and Triton's orbit is slowly decaying. In a few billion years, Triton will either crash into Neptune or be torn apart by tidal forces, forming a spectacular ring system around the planet. Triton has geysers like Enceladus, but instead of water, they erupt with nitrogen gas. The geysers create dark streaks on Triton's icy surface as nitrogen carries dark particles high into the thin atmosphere before they settle back down. Triton might have a subsurface ocean heated by tidal forces, though this is speculative. Neptune also has faint rings, discovered in the 1980s. The rings are patchy, with some sections much denser than others, creating arc-like segments rather than complete circles. Neptune marks the edge of the planetary realm, the last of the 8 major planets. Beyond it, the Sun's influence weakens, but it doesn't end. Space doesn't simply stop at Neptune's orbit. There's still more to explore, though what lies beyond is different. No more giant worlds of gas and cloud. Instead, we enter a realm of ice and silence where small, frozen bodies drift in orbits that take centuries to complete. Let your thoughts drift past Neptune now, into the frozen outer reaches where darkness deepens and the solar system begins to fade into the void. This is where we find the leftover pieces, the icy remnants that never became planets. Beyond Neptune lies the Kuiper Belt, a vast region of space filled with icy bodies, remnants from the solar system's formation. The Kuiper Belt extends from about 30 astronomical units, roughly Neptune's orbit, out to about 50 astronomical units. To give you a sense of that distance, if Earth's orbit around the Sun were the size of a dinner plate, the Kuiper Belt would extend from about 1.5 meters to about 2.5 meters away. It's a vast, cold region where sunlight is faint
and temperatures hover just a few dozen degrees above absolute zero. The Kuiper Belt is similar to the Asteroid Belt in some ways, but far larger in extent and composed mostly of ice rather than rock. It contains hundreds of thousands of objects larger than 100 kilometers across, and millions of smaller ones. These are icy worlds, frozen mixtures of water, methane, ammonia, and rock, preserved in deep freeze since the solar system's formation 4.6 billion years ago. The Kuiper Belt is named after Gerard Kuiper, a Dutch-American astronomer who, in 1951, predicted the existence of a belt of icy objects beyond Neptune. At the time, it was pure theory, but in 1992, astronomers discovered the first Kuiper Belt object beyond Pluto, confirming Kuiper's prediction. Since then, thousands have been found, and we've realized that Pluto, once considered the ninth and outermost planet, is actually just one of the largest members of this vast population. The most famous Kuiper Belt object, by far, is Pluto. Discovered in 1930 by Clyde Tombaugh, a young astronomer working at Lowell Observatory in Arizona, Pluto was immediately hailed as the ninth planet, a distant, mysterious world at the edge of the solar system. For 76 years, from its discovery until 2006, Pluto held that status. Children learned the 9 planets, memorizing their order, often using mnemonics like, "My very educated mother just served us 9 pizzas." But as astronomers discovered more objects in the Kuiper Belt, some comparable in size to Pluto, it became clear that calling Pluto a planet while ignoring similar objects was arbitrary. In 2005, astronomers discovered Eris, a Kuiper Belt object, slightly smaller than Pluto but more massive. This forced a reckoning. Either Eris and potentially dozens of other large Kuiper Belt objects would have to be called planets, or Pluto's status needed reconsideration. In 2006, the International Astronomical Union convened to define, for the first time formally, what a planet is. They established 3 criteria. A planet must orbit the sun. It must be massive enough for its gravity to pull it into a roughly spherical shape. And it must have cleared its orbit, meaning it's gravitationally dominant in its orbital zone, having absorbed or ejected most other objects. Pluto meets the first 2 criteria but fails the third. Its orbit is populated with thousands of similar objects. It hasn't cleared its neighborhood. So Pluto was reclassified as a dwarf planet, a new category for objects that are round but haven't cleared their orbits. The decision was controversial, and many people still feel nostalgic affection for Pluto's planetary status. But scientifically, the reclassification makes sense. Pluto is better understood as the king of the Kuiper Belt rather than the runt of the planets. Pluto is about 2,370 kilometers across, roughly 2/3 the diameter of Earth's moon. It's so small that 7 Plutos could fit side by side across Earth's diameter. Yet, for its size, Pluto is remarkably complex. When NASA's New Horizons spacecraft flew past Pluto in July 2015, after a journey of 9.5 years, it revealed a world far more geologically active and diverse than anyone expected. Pluto's surface is a complex mix of frozen nitrogen, methane, and water ice. Nitrogen ice, in particular, dominates much of Pluto's appearance. There are vast plains of frozen nitrogen, smooth and relatively young, with few craters. These plains, part of a large heart-shaped region called Tombaugh Regio, in honor of Pluto's discoverer, show that Pluto has been geologically active relatively recently, at least in geological terms. Sputnik Planitia, the left lobe of the heart, is a basin filled with nitrogen ice that appears to be slowly flowing, like a glacier, though at Pluto's frigid temperatures, nitrogen ice is the consistency of soft rock. The ice in Sputnik Planitia is organized into polygonal cells, each about 10 to 40 kilometers across, created by convection. Warmer ice rises from below, spreads out at the surface, cools, and sinks back down, creating the cellular pattern. This kind of convection requires an internal heat source, and scientists think it might be powered by the slow decay of radioactive elements deep in Pluto's interior. Pluto also has mountains made of water ice, which at Pluto's temperatures is as hard as rock. These mountains reach heights of 3,500 meters, taller than the Rocky Mountains on Earth. The mountains are relatively young, with few craters, suggesting they formed within the last 100 million years or so. Some of them have unusual jagged peaks that look like they were recently carved out. There are also hints of cryovolcanoes on Pluto, volcanoes that erupt not lava but a mixture of water ice, nitrogen, ammonia, and methane. One mountain, Right Mons, is a possible cryovolcano. It's about 4 kilometers tall with a central depression that could be a caldera, though this interpretation is still debated. Pluto has a thin atmosphere, mostly nitrogen, with traces of methane and carbon monoxide. The atmosphere is tenuous, about 100,000 times thinner than Earth's, but it extends surprisingly high, creating a blue HAZ layer, visible in images taken by New Horizons. This haze is created by sunlight, breaking apart methane and nitrogen molecules, which then recombine into more complex organic compounds that scatter blue light. Pluto's atmosphere is not constant. As Pluto moves along its highly elliptical orbit, its distance from the Sun changes significantly. When Pluto is closest to the Sun, at perihelion, it's about 30 astronomical units away. At aphelion, it's nearly 50 astronomical units away. When Pluto is closer to the Sun, its surface warms just enough for some of the nitrogen ice to sublimate, turning from solid to gas and creating a thicker atmosphere. When Pluto moves farther from the Sun, the atmosphere freezes out, snowing back down onto the surface as frost. Pluto has 5 known moons. The largest, Charon, was discovered in 1978. Charon is about 1,200 kilometers across, making it more than half Pluto's diameter. The size ratio between Pluto and Charon is so unusual that some astronomers prefer to call them a binary system rather than a planet and moon. The center of mass, around which they orbit, called the barycenter, lies in the space between them, not inside Pluto. They're locked in synchronous rotation, always showing the same face to each other. If you stood on Pluto, Charon would hang motionless in your sky, never rising or setting, fixed in the same position forever. Charon's surface is different from Pluto's. It has fewer bright nitrogen ice plains and more water ice and dark material. Charon also has a massive canyon system, Serenity Chasma, about 1,900 kilometers long and 9 kilometers deep, dwarfing Earth's Grand Canyon. This canyon may have formed when a subsurface ocean froze and expanded, cracking the crust. The other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller, irregularly shaped, and probably captured Kuiper Belt objects that wandered too close and were gravitationally bound. They all have unusual orbits, tumbling chaotically rather than rotating tidally like most moons. Other dwarf planets exist in the Kuiper Belt. Eris, discovered in 2005, is about 2,326 kilometers across, roughly the same size as Pluto, but more massive. Eris is one of the most distant objects known, currently about 96 astronomical units from the Sun, nearly 3 times farther than Pluto. Its surface is covered in methane ice that appears exceptionally bright and reflective, suggesting the surface is relatively young and frost-covered. Makemake, discovered in 2005 and named after a creation deity from Easter Island, is about 1,430 kilometers across. It's the 3rd largest known dwarf planet. Its surface is covered in frozen methane and ethane, and it has at least 1 small moon. Haumea, discovered in 2004, is one of the strangest objects in the solar system. It's elongated, shaped roughly like a rugby ball or an American football, about 2,000 meters long and 1,000 meters wide. This odd shape is caused by its incredibly fast rotation. Haumea spins once every 4 hours, so fast that centrifugal force has pulled it into an elongated shape. It also has a ring, making it one of the few objects beyond the giant planets known to have rings. Haumea has 2 small moons, Hi'iaka and Namaka, named after daughters of the Hawaiian goddess Haumea. The Kuiper Belt gradually fades into the scattered disk, a region where objects have more elliptical and inclined orbits, probably scattered outward by gravitational encounters with Neptune. Early in the solar system's history, these objects can have orbits that take them far beyond the Kuiper Belt before swinging back in. Eris is part of the scattered disk, which is why its orbit takes it so far from the Sun. Beyond the scattered disk lies the Oort Cloud, the outermost region of the solar system. We're reaching the very limits of the Sun's gravitational influence now. Take a breath. Let your mind drift through this distant realm of ice and darkness. We're approaching the edge, the boundary between what belongs to our Sun and what belongs to the galaxy beyond. Comets are icy visitors from the outer solar system. When a comet's orbit brings it close to the Sun, solar heat causes the ice to sublimate, turning directly from solid to gas. This creates a glowing cloud around the comet's nucleus called a coma, and often a tail that stretches millions of kilometers, blown outward by the solar wind and radiation pressure. Comets come from 2 main regions. Short-period comets, which orbit the Sun in less than 200 years, originate in the Kuiper Belt. Long-period comets, which can take thousands or even millions of years to complete an orbit,
come from the Oort Cloud. The Oort Cloud is a theoretical shell of icy objects surrounding the entire solar system at distances between 2,000 and 100,000 astronomical units. That's nearly 2 light years from the Sun, almost halfway to the nearest star. Objects in the Oort Cloud move so slowly and are so distant that they're barely bound to the Sun. A passing star could easily disturb them, sending some on trajectories that bring them into the inner solar system as comets. The Oort Cloud has never been directly observed. It's too distant and too faint. But the orbits of long-period comets all point to an origin in this distant region. So astronomers are confident it exists. Imagine the Oort Cloud as a vast spherical shell enclosing the solar system, a halo of frozen worlds drifting in the darkness, so far from the Sun that they're lit only by starlight. It's the final frontier of the Sun's gravitational influence. Beyond it lies interstellar space, the realm between stars where the Sun's gravity gives way to the gravity of other distant suns. Let your mind rest on that image for a moment. The solar system from the blazing Sun to the frozen Oort Cloud, an immense structure spanning nearly 2 light years, and yet just a tiny bubble in the vastness of the galaxy. Take a breath. We've traveled far tonight, from the center of our cosmic home to its outermost edge. Now, as our lecture draws to a close, let's reflect on what we've seen and what it means. The solar system is our home, but it's just one system among billions. The Sun is one star out of hundreds of billions in the Milky Way, and the Milky Way is one galaxy out of hundreds of billions in the observable universe. The scale is almost incomprehensible. Yet here we are, on the third planet from an ordinary star, conscious and aware, looking out at the cosmos and trying to understand it. We've sent spacecraft to every planet. We've landed rovers on Mars, dropped probes into Jupiter's atmosphere, and flown past Pluto. We've looked deep into space with telescopes, seeing galaxies billions of light years away. And we've looked inward, studying the atoms and molecules that make up our world and ourselves. The solar system is more than just a collection of objects orbiting the Sun. It's a dynamic, interconnected system shaped by gravity, light, heat, and time. The Sun's gravity holds everything together. Its light and heat drive weather, climate, and life on Earth. The planets influence each other through gravitational interactions, subtle tugs that shift orbits over millions of years. The solar system has a history. It formed about 4.6 billion years ago from a collapsing cloud of gas and dust. The Sun ignited at the center, planets coalesced from the remaining material, asteroids and comets, leftovers from this process, have been colliding and evolving ever since. Life emerged on Earth, a remarkable development that, as far as we know, happened only here. But the discovery of subsurface oceans on moons like Europa and Enceladus, and organic molecules on Titan and in comets, suggests the ingredients for life are common. Whether life itself is common remains one of the great unanswered questions. the solar system will continue to evolve. The sun will gradually brighten, making Earth uninhabitable in about 1 billion years. In 5 billion years, the sun will swell into a red giant, consuming the inner planets. The outer planets and their moons will remain, drifting in orbit around a white dwarf, the fading remnant of the sun. Eventually, even the white dwarf will cool, and the solar system will become a dark, frozen collection of worlds orbiting a dead star. But that's billions of years away. For now, the solar system is alive, dynamic, full of worlds waiting to be explored. And we're here, part of it, looking up and wondering. And that brings us to the end of tonight's syllabus. We've traveled from the sun to the edge of the solar system, visiting rocky worlds, gas giants, icy moons, and distant dwarf planets. We've seen storms larger than Earth, volcanoes erupting on alien moons, and rings of ice circling giant worlds. We've witnessed the diversity and wonder of our cosmic neighborhood. The solar system is your home address in the universe. You live here on a small blue planet, orbiting an ordinary star in an ordinary galaxy. But there's nothing ordinary about being here, about being alive, about being able to look up and understand even a little the vast clockwork of worlds spinning through space. As you drift towards sleep now, picture yourself floating above the solar system, looking down on the sun and its family of planets. See the inner rocky worlds, close and warm. See the Asteroid Belt, that band of ancient rubble. See the giant planets, Jupiter and Saturn with their moons and rings, Uranus, tilted on its side, and Neptune, cold and blue at the edge. And beyond, the Kuiper Belt and the Oort Cloud, fading into the darkness of space. You are part of this system. You're made of elements, forged in stars that lived and died billions of years ago. You're standing on a planet that's been orbiting the sun for 4.5 billion years. And you're looking up at the same sky that countless humans have gazed at across thousands of generations, wondering about the lights moving among the stars. There's no homework tonight, no assignments to complete, just rest. Let your mind wander among the worlds we visited. Let the vastness of space become a gentle backdrop to your dreams. The solar system will still be here tomorrow, spinning silently through the galaxy, waiting for you to look up again. At the School of Nap, every student passes. Sleep is always the right answer. And tonight, you've earned it. Class dismissed. Sleep well, students. See you among the stars. Good night.